two parts. Okay. Time domain analysis of control system. Okay. It is divided into two parts. The first one is transient response. Second one is steady state response. Okay. So full complete time domain response CT is a addition of transient response plus steady state response. Okay. We will see both transient response and steady state response separately. So what is transient response? See, a transient response is a response which dies out or becomes zero after a large interval of time. Okay, mathematically I can write it as limit at t tending to infinity Ct t is equal to 0. Okay, and what is then steady state response? A steady state response is simply the part of the total response that remains affect the transient has died out. Okay, when transient response has died out, so whatever is remaining, that is a steady state response. First point, transient response is defined as the part of the time response that goes to 0. Okay, it becomes 0 after a large time interval. This large time interval depends on the time constant. Okay, so on the depending on the time constant, after 5 time constants, 6 time constants, or 10 time constants, it will achieve a steady state response approximately. Steady state response is the part of the total response that remains after the transient response has died out. Okay, so total time response is sum of steady state response plus transient response. Okay, now uh, now to carry out the time domain analysis, there is few important test signals. Okay, the first one among them is step input. Step input function, mathematically it can be written as is equal to some function a for t greater than equal to 0 and it equals 0 otherwise. Okay, I can draw like this. Okay, this is my RT. This is a step input function. The second one is ramp input function. A ramp input function RT equal to interval. It can be drawn like this. The slope of this line will depend on the R. Okay. Third one is parabolic input function. R t square for t greater than equal to 0 and 0 otherwise. If I draw figure for this, it will be something like this. Okay. Okay. So these are the three different type of standard test signals which we will use while doing our time domain analysis. Now the important point here is why only these three types. Okay. The reason is these three types are so general test signals. We can create many test signals. We can create any test signals using these three standard test signals. Okay. We will see this thing when we will do certain problems, that certain test signals containing can be made using step, ramp and parabolic. Okay. Write note first. Step input function. This particular step input helps in knowing the system's quickness. Fastness, I can say like, because since the step input function is having an abrupt jump from 0 to certain finite value, to this particular thing, how the system is behaving can be understood by this particular step function. Second, ramp input function, it helps in knowing system, how the system would behave to a signal that changes linearly with time, because ramp input function changes linearly with the time. Okay. System behavior to signals that changes linearly with time. Third one, parabolic is just 1 degree higher than the ramp. And they have got similar function what the ramp input function is having. Only thing is that they are 1 degree higher than the ramp input than the ramp input function. Okay. Now we will see the steady state analysis first. Okay. In steady state analysis, we will be more concerned about the steady state error, because finally it is since my final output of the system is going to achieve some steady state, then the difference between the expected and the difference between the final outcome, that gives me the steady state error. From the input, how much it is deviating, that gives me the steady state error. Okay. So before starting the steady state error, I'll take a closed loop negative feedback control system. all analysis are done for a negative feedback control system, because positive feedback control systems are unstable, and in that case steady state error is always going to be infinite. This is error ET, error Laplace transform ES, CT, CS, DT, BS. Okay. Now I know this, my ET is equal to RT minus BT. Okay. Means ES equal to RS minus PS. Okay. I can write BS as HS into CS. Okay. From this, I will get my ES is equal to RS upon 1 plus GS into HS. Okay. Very important. Error at steady state is equal to limit t tending to infinity ET. So whatever is my ET, if I want to find the steady state error, I just need to find the value of this limit. Okay. Using the final value theorem of Laplace transform, ESS is also equal to limit s tending to 0 s into ES. Okay. So I can finally write my steady state error is equal to limit s tending to 0 s into Rs upon 1 plus GS HS. Okay. Now, this steady state error depends on the reference input Rs and the loop transfer function GS and HS. Okay. So loop transfer function, it depends on loop transfer function GS into HS. Difference input RS. Since RS, we are going to take the three different types: step, ramp, and parabolic. But the transfer function GS HS is also depends on the GS. Now, if my GS HS, now I have to see for the type of the control system. What is the type? So if I having my GS HS of something like this, then my type is 2. It is the power of S term which is there, that is the type. If it is K S plus 1 upon 1 plus 2S, that means here type is 0. Okay. If I am having type is 1, here the power of S is 1. Okay, understood. So this is the type of the system. So I can write type of a system refers to order of the pole of ESHS at s equal to 0. All are at s equal to 0 only. Here 2, here 0, here 1. Okay, 2, 0 and 1. So depending on that, the type is defined. Okay, so this is the type. Now we will take the first case of a steady state error of a system with step input function. First one, steady state error of system with step input. We'll see for the various types, but the input is step. Okay. See, we know ESS is equal to limit s tending to 0 s into Rs upon 1 plus Es into Hs. Now Rs, since it is a step, so it will be R by S. So my ESS will become, in this case, limit s tending to 0 s into R by S upon 1 plus Gs into Hs. Okay, R, this s and this will get cancelled, so this will be limit s tending to 0 R upon 1 plus Gs into Hs. Okay, so my steady state error now depends only on the Gs into Hs. Okay, so I can write this as R upon 1 plus limit s tending to 0 Gs into Hs. So this is known by position error constant, which is equal to s tending to 0 Gs into Hs. So I can write my steady state error R upon 1 plus Kp. Now this is assuming when the type of the system is 0. Okay, type in this case of this is 0. Now in case if type is 1, then what will happen? Then GSHS will have s in the denominator. Putting s in the denominator will make my KPS infinity. So in that case, for type 0, ESSS R upon 1 plus Kp. For type 1, ESS equal to R upon 1 plus infinity equal to 0. Because Kp in that case, just write a note, limit s tending to 0 G dash S H dash S upon S. This S, which is in denominator, will make my whole term as infinity. Okay, that means only for type 0 ESS is finite, or other type 1, type 2 ESS is going to be 0 only, and Kp is infinite. Okay, so this is for the steady state error for the step input. Now we will take another case for the ramp input. Second one, steady state error of a system with ramp input. Again, a ramp input is written by k by s square. Okay, so in this case it will be ESS is equal to limit s tending to 0 s into Rs upon 1 plus Gs into Hs. So it can be written as substituting the ramp input transfer function s into a by s square upon 1 plus Gs into Hs. So this is limit s tending to 0 a by s upon 1 plus Gs into Hs. Okay, now 1 by s. Okay, so this, in case, I can write it as like this: a upon s plus s into gs hs. ESS will become a upon s gs hs limit s tending to 0. Now, if my GSHS is of type 0, in that case, there will be no term in the denominator. There will be no S term in the denominator. Means simple S. There is no pole at origin in the denominator. In that case, GSS will become A upon 0 equal to infinity. For type 1, okay. In this for type 1 system, there will be a single pole at the denominator, single pole at the origin. That means that S and this S will get cancelled, and I will have A upon kV, where kV is equal to limit S tending to 0 gs into hs. Okay, S into gs into hs. For type 2, there will be two poles at origin. At that point, it will be A upon infinity is equal to 0. So this is the steady state error for ramp input in case of for ramp input, okay, for different cases of type 0, type 1 and type 2 system. This kV is called velocity error constant. Now if we look for a previous case for step input, if I am having an input like this, then my output is something like this. This point is a steady state error. Okay, and this is equal to R upon 1 plus Kp, is position error constant. My reference input R, right? Output. In case of parabolic, in case of ramp, my input is this, okay? Output is going to be something like this. This particular error is equal to A by Kv, where Kv is a velocity error constant. In this case, due to step input, if I give as an input to this as a to system, then it will keep on rising. The step input is this. At some point, this error will become infinite. Okay, that's why for step input with type 0, error is going to be infinity. But for type 2, error is again 0. Okay, now we'll see the third case. The steady state error we have to find with respect to parabolic. Okay, see, RS in case of a parabolic input is 2R upon SQ. So substituting this in ESS, limit S tending to 0, S 2R upon X cube over 1 plus GS into HS. I will have this as 2R upon S square 1 plus GS into HS. Limit S tending to 0. Okay. So I can write my ESS nothing but 2R limit S tending to 0 S square GSHS. Now if my GSHS of type 0, ESS is going to be infinity. For type 1, ESS again going to be infinity. For type 2, ESS is going to be finite and that is equal to 2R by K. Okay. Where K is acceleration error constant, K is equal to limit S tending to 0 S square GS into HS. For higher type, for type 3 and above, ESS is going to be 0. Okay. Now, this is the case with parabolic input. Note. To summarize all the things, I'll write here type of system KP, KV and KK. Type of system 0, KP is some constant K, this is 0. Type of system is 1, KP is infinity and 0. Okay. Type of system is 2, is going to be infinity, this is going to be infinity, this is going to be some constant K. Type of system is 3, infinity, infinity, this is also going to be infinity. There will be some other constant which is having some finite value. In this case, steady state error for all the three we can find out. So this can come as a 1 mark question. Okay. Note 2. This particular type of error constants are applicable only to the given configuration. The configuration what we have chosen is GS upon 1 plus GS into HS. If configuration is different, then definitely the error constants will also be different. Okay. It is applicable only to particular configuration. Next, in case if system configuration is different from the, I can write for the previous one, it's applicable only to particular configuration, that means particular configuration shown like this. Okay. Now, in case if configuration differs from the given configuration, from the very particular general configuration, then we have to establish a relationship for the error signal. Okay. On finding the error signal, we can find the error by using the final value theorem of Laplace transform. For any general configuration. steady state error of a system with an input that are linear combination of the basic types can be determined simply by superposing all the different steady state errors. Different steady state error. State error. That means, suppose my input signal xt is t plus t square by 2 plus 1 for t greater than equal to 0 and equal to 0 otherwise. Then, since my xt is a linear combination of ramp, parabolic and step, I can find my ESS for ramp plus parabolic plus step together. Okay. So in this way, steady state error can be found. We will see this when we will solve problem. How to find steady state error in such case. It is just a linear. It is just a superimposition of the various steady state error case. So this is about the steady state error, which is a part of steady state analysis in time domain analysis. Okay. Next topic will be the transient response analysis.